All right, so let's do this. So today we're going to get started on our next chapter, but before we do that, I actually want to take some time here at the beginning to just review what it is that we learned last week with regard to these reactions. We got our first taste of reactions in this course, and so let's just kind of do a little bit more practice before we move on. All right. Okay, we're going to take a conjugated diene here. We're going to react it with one of those hydrohalogens like HBr. All right, and everybody's going to take a second and give me the 1,2 and the 1,4 adduct that we would expect in this reaction here. All right, so in this case we have this symmetric diene here, so I can sort of pick whatever direction I want to number and I would get the same product. If I'm going to do my 1,2 adduct, that means that my hydrogen and my carbon are added 1, 2 carbons away from one another. My hydrogen and my bromine are added 1, 2 carbons away from one another. And importantly, the bromine is always going to go in that allylic position. So the bromine's on carbon 2. My hydrogen, I can draw it in explicitly if I want, but I don't have to, is living over here on carbon 1. Okay. For the 1,4, let's actually do our mechanism here. This is a reaction where, not all reactions that we study are going to have a mechanism for, but this is one where we do indeed have a reaction mechanism. So let's go ahead and do that for our 1,4 adduct. All right, so my nucleophile, the electron-rich species here, is that conjugated diene, and specifically that pi bond. It's glowing red hot with that electron density. And it's going to attack our electrophile in this reaction, that hydrogen, which is left relatively electron deficient because of that polar bond with bromine. So our first step here is nucleophilic attack. All right, but we can't stop there. Hydrogen would be breaking its octet rule. So we're also going to have to break that hydrogen-bromine bond. Okay. If we look at our intermediate here, right, there are two possible locations where we could put that hydrogen on either side of this double bond here. All right. One carbon will get the hydrogen, the other one will be left without that pair of electrons and have a carbocation. All right, so where's the hydrogen going to go? Green or orange?
Green.
Green. because our carbocation has to form in that allylic position. All right, so this is a very important feature of our reaction mechanism here, and this intermediate, it informs the regioselectivity of this reaction, why bromine's going to a particular location, this allylic carbocation. Right, super important intermediate here. All right, and if the bromide ion attacks that carbocation, boom, we got our 1,2, right? But we're going for the reaction mechanism of our 1,4. So now we need to show through resonance. All right, everybody take a second and see if you can't show me the resonance of that pi bond and that carbocation. Right, filling in electron pushing arrows, and then finally the product of that step or our other intermediate. Okay. Remember, we looked at these pi bonds in terms of the orbitals, the overlap of these peanut-shaped p orbitals. This is what's forming that pi bond, okay? And this is really ugly. I'm going to get rid of this in a second. But importantly, one of the things that you studied about carbocations at the very beginning of this course, or of your organic chemistry career, is that carbocations are one of the weirdest things in organic chemistry, in that it's like one of the only times we see an element with its octet rule violated. Right? A carbocation is carbon with 3 bonds and no lone pairs. So it's only got 6 electrons in that octet, which means that it has this empty p orbital right here, right next door, ready to accept that pair of electrons from that pi bond. All right? So these carbocations here, they accept pi electrons really easily, and that's what we're going to show here. Our arrow is going to start at that pair of electrons, and it's going to end at the atom that's accepting that pair of electrons. All right, and so this will have the effect of having that double bond and that carbocation kind of swap places. Right, so now my carbocation is located up here, and my pi bond has moved. Okay. So then if we're going to finish this off, we need that bromide ion back. That's now going to be our nucleophile. Now this bromide ion with this negative charge is glowing red hot, and we have our carbocation, which is left relatively electron deficient. Right? And so my electron pushing arrow here will start at that pair of electrons, that lone pair, and go and attack that carbocation. All right, so our 1,4 product here, we have a hydrogen on carbon 1. Our bromine's now located all the way over here on carbon 4. And importantly, our pi bond has also moved because of that resonance step. Okay. Let's just go ahead and put this back up here next to its other one. Okay. And so then lastly, we can ask sort of like, okay, let's say that we carried out this reaction at low temperatures. What would be our major product here, the 1,2 or the 1,4?
1,2.
1,2, what we would call our kinetic product. All right, and then what about our thermodynamic product? Is that always 1,4? No, we got to go and compare these two structures here. It might be the 1,4, but it also might not be, right? We got to compare these two structures, and we have to figure out which one is more stable. And remember, my more stable, I'm really looking at the substitution of that double bond. This one right here, the 1, 2, what would we classify that double bond as? Mono, di, tri, tetrasubstituted. It's tri, right? So if we look at these two carbons, our two sp2 carbons, and we count how many carbon neighbors they have, this one would be tri-substituted. And what about our 1, 4? Tetra. So if we look at these two, now we have all, fully filled out 4 neighbors. So which one's more stable, tri or tetra? Tri, so that, tetra, okay, the more substituted one. Cool. So that means our high temperature product or our thermodynamic product is indeed the 1, 4 in this case. But again, that's not always the situation. Cool. All right. So symmetric conjugated diene, kind of best case scenario. There's only one possible 1, 2 product and one possible 1, 4 product. Let's take a look at another example here. Now we're going to make it asymmetric. We'll stick pretty similar. Okay. Again, we're going to react this with HBr. All right, but now that we have this asymmetric conjugated diene, it's going to depend on whether we look at this and number 1, 2, 3, 4, or we go the other direction, 1, 2, 3, 4. We'd get a different 1, 2 product from the red numbering than we would for the blue numbering. All right, so looking just at the 1, 2 adduct, everybody take a second and draw me these two possible products here. All right, so if I do look at my red numbering, I'm going to put hydrogen on the red carbon 1 and bromine on the red carbon 2. And if I do my other product, where my other double bond is playing the role of the nucleophile, now my bromine's on blue carbon 2 and my hydrogen is on blue carbon 1. Okay, so these are both the 1, 2 product, just depending on which one of those two bonds plays the role of the nucleophile. So then if I want to know which one of these is going to be my major product at low temperatures, right, it's always going to be one of these two options because these are my 1, 2. But I got to now look at my intermediate here, right? Whichever one of these is the more stable carbocation will have the lower activation energy. So I'm going to compare that one to my intermediate of my 1, 2 over here. Okay, both of these are allylic. They got to be allylic. All right, but then the question is, which one is more stable than the other? So if we look at this red one here, it's allylic. And what would we classify this carbon as? Primary, secondary, or tertiary? Secondary. So it's a secondary allylic carbocation. And what about the blue one here? What would we classify this carbon as? Primary, secondary, or tertiary? Also secondary. So they're both secondary allylic carbocations. So then both of these will be produced in just about a 50-50 mixture. So we're going to include both of them as our major product. One of them is not more favored than the other. All right, and we can just make a note for that kinetic product. We had to compare the carbocations of our 1, 2 atoms. All right, so for the sake of kind of not having this get too busy, we're going to do the thermodynamic product, but I'm just going to kind of copy and paste. So we're not trying to scrunch all this in there. Okay. For our thermodynamic product, we got to compare all of our possibilities, right? So we got 2 of them. We got our 1, 2s. Now we need our 1, 4s. And we're going to have to look at all 4 of these and compare to figure out what our major product is. So you took a second and gave me the 1, 2s. Now take a second and give me the 1, 4s for this reaction as well. All right, so if I'm going to do my 1, 4 product from the red numbering, my hydrogen's going to go on carbon 1. My bromine is going to go all the way on the other side on carbon 4. And as we illustrated with our mechanism in the last example, that double bond is also going to move to be between carbons 2 and 3. If I want to draw my other 1, 4 product, my hydrogen is now on my blue carbon 1. My bromine is on blue carbon 4. And again, that double bond has moved. Okay, so now I have to compare all 4 of these and figure out which one is the most stable, which one is going to be preferred at high temperatures. And again, by most stable, we really mean the more substituted alkene. So we're going to go and look at all these double bonds here, and we're going to classify them as mono, di, tri, or tetra substituted. Okay. Everybody take a second and see if you can't do that and finally answer me what the major product is at high temperatures. All right, I'm going to kind of quietly go in and fill in here. So this very first one that we did is a tri-substituted alkene. Those sp2 hybridized carbons have 3 carbon neighbors. All right, our other 1,2 product was a di-substituted alkene. And both of our 1,4 products are also di-substituted. All right, so then out of these 4 here, which one is going to be the most stable? That tri-substituted one, right? So we will get just this one major product if we carry this out at high temperatures. Our most stable product here. In this case, it's not one of the 1,4s. It's our 1,2, and only one of them. Okay? So at low temperatures, when we carried out this reaction, we got a mixture of both of our 1,2 products. These are our kinetic products. We carry out the same reaction at high temperatures. Now we're going to select just one of those 2 that's going to be our major product. Okay? And again, for our thermodynamic product, what do we do? All right, we got to draw them all. And determine which is the most stable. Which again, in terms of alkenes, means the most substituted. Cool. All right, we also talked about another type of reaction, this electrocyclic reaction or Diels-Alder reaction, where we take our conjugated diene and we react it with something we call a dienophile, and we're always going to get these 6-membered rings out of this reaction here. Okay? When we line everything up like this in this conformation, specifically the conformation of our conjugated diene, it's a little easier to tell where that 6-membered ring comes from that we get on our product side. But this is a ridiculous way to draw that molecule, right? Nobody actually draws it like that unless you're about to do a Diels-Alder reaction, okay? So how do we go from our normal way of looking at a molecule? So for example, 1,2-butadiene, we would draw in our straight chain. Okay, but if we wanted to use this in a Diels-Alder reaction, we would want to kink that about that single bond. Okay, and so to be clear, how do we get from one conformation to the other? These are just different rotational states of this same molecule. Remember, you're not allowed to rotate about a double bond, but you can absolutely rotate about a single bond. All right, and so that's exactly what we did here in order to get our conformation that we want when we do our Diels-Alder reaction. Okay, we do have fancy names. This is what we would call the S-trans conformation and the S-cis conformation. This is often one of the limiting steps or one of the limiting factors in a Diels-Alder reaction is this rotation right here. Things are more stable in the S-trans conformation than the S-cis. So these reactions tend to be quite slow. If you have a molecule that's actually locked in that S-cis conformation, like there's a ring or something like that, they tend to be orders of magnitude more reactive in a Diels-Alder reaction just because they already have the correct configuration here. All right? But how are we, so in this particular example, it's not quite as bad to see how we've rotated, but what if we have something a little bit bigger and uglier? Okay, so let's say that we want to react this molecule our dienophile and figure out the product of our Diels-Alder reaction. All right, so again, the first step is we're going to want to rotate this into that S-cis conformation by going about that carbon-carbon single bond in our conjugated diene. All right, so first of all, if you have like a model kit, that's what these things are perfect for, right? Is seeing how these molecules can rotate about their single bonds, okay? But you know, we don't have a model kit here, so a few tricks that we can use. So first of all, also the name of the molecule will be consistent. So if we find our parent chain, 1, 2, 3, 4, 5, 6, with these two methyl groups, right? That better be the same. Okay, so let's start in that kind of conformation where we want, okay, we want our double bonds facing the same direction. All right, but we got to add a bunch of stuff here, okay? Okay, these 1, 2, 3, 4, these are going to be the 4 that participate in this Diels-Alder reaction, the 4 sp2 hybridized carbons about my double bonds here. All right, but I need to add some stuff on here, right? So everybody take a second, see if you can't fill this out. The one thing that I will say that we can make sure that we've rotated correctly is not only, you know, you name the molecules the same, but also the stereochemistry of each of your double bonds has to remain consistent. My double bond, the two methyl groups are pointed on the same side in this molecule. That better be the case in my once I rotate it as well. Same thing over here. My two methyl groups pointed on the same side, right? Both of these are in this E stereochemistry. They better be in the E stereochemistry when I rotate it as well, okay? So everybody take a second. See if you can't fill this in our molecule. This exact same molecule, you've just rotated it about one of those bonds in the middle. All right, carbon 1 had a methyl group, carbon 2 also had a methyl group, and again, they need to be pointed on the same side, just like they were in my original molecule. Likewise, carbon 3 has this methyl group, and 4 has a methyl group, and again, those two are pointed on that same side. Okay? So now we'll take this and we'll react it with our dienophile. We'll put that in that right conformation as well, so it's a little bit easier to see how these things are going to be linked up. And everybody's going to take a second and give me the product of this Diels-Alder reaction. All right, so remember the easiest way to do this is to actually start with what you know your product is going to be, that 6-membered ring. All right, and then we're going to try to map carbons from the left to the right here. I know that 4 of these carbons were the 4 from my conjugated diene. The other 2 would then be from that dienophile. Okay. In this case, I got methyl groups on all 4 of those carbons in my conjugated diene. All right, one other thing to note about our reaction, we have 2 electron pushing arrows that are the creation of these 2 new sigma bonds, but there's a third as well, which corresponds to the movement of that pi bond. So in my product, I need this new pi bond between carbons 2 and 3. All right. And then the last thing about these is that they preserve the stereochemistry of your dienophile. So because I'm starting out with this cis alkene here, I need to have that reflected in the stereochemistry of my product, where both of those chlorines are on the same side of this ring, either both on wedges or both on dashes. It doesn't matter which one. All right, but we got to indicate that they're pointed on the same side. Okay, because we started out with a cis dienophile, we're going to get a cis ring. All right, cool. So we have our normal way that we draw our molecules that are in their most stable extended form, but in order to react in a Diels-Alder reaction, they have to kink themselves into this S-cis conformation before they can react. All right, we're also going to note in this example was a good example of how our Diels-Alder reactions preserve stereochemistry. We started out with this cis dienophile, so we have a cis product as well, where both of those chlorines are pointed on the same side of that 6-membered ring. Okay, this rotation step, again, as I mentioned, it's kind of the limiting step in a lot of reactants, a lot of conjugated dienes and Diels-Alder reactions. You may or may not, because it works very well, do a Diels-Alder reaction in lab, and you're almost guaranteed to use a diene, a conjugated diene, that is locked in that correct conformation because of a ring, right? So something like cyclopentadiene here, it's already in that correct S-cis conformation, so we can react this with a dienophile. Okay. I'm going to turn this to the side so we can see it a little bit easier in terms of how it's going to react. All right, I'm going to do my product is, again, that 6-membered ring. Okay. These 1, 2, 3, 4 carbons about those conjugated pi bonds are going to be my 1, 2, 3, 4 carbons over here. I got my 2 carbons in my dienophile. Okay. I'm going to number here just so we can keep extra special account of what's going on here. I need a new pi bond in this molecule between where? Carbons what and what? Carbons 2 and 3. All right, but I'm also missing something else here, right? If I look, I've got this 1 carbon on the left that is not featured anywhere on the right-hand side, right? I need to draw that in. Well, there's a bond between that green carbon and carbon 1, as well as carbon 4, and that's exactly what we're going to do. Boom. These are really ugly. They look very terrible on 2 dimensions on pencil and paper. If you build them in like 3 dimensions, they look like kind of like little spheres. All right, we would call these, this is a bicyclic compound or a fused ring. All right, they're a pain in the butt to draw in 2 dimensions, but they're pretty cool. And yes, this would indeed be a product. This thing forms in like 3 seconds. You get a super high yield. This reaction is super efficient because you're starting out with a conjugated diene that's already in that correct S-cis conformation and can't rotate out of it, right? It's stuck in that conformation because it's in this ring here, okay? But yes, we do get this ugly product, this fused ring. We have that carbon still right in the middle of carbons 1 and 4. Cool. All right, so just to do a few more examples of these reactions, these are the first reactions that we've covered in this course. Reactions are obviously a tricky bit in organic chemistry. One more thing before we move on, a lot of people ask me, like, how do I keep all these reactions straight in my head? For me, the category of those reactions, right? Electrophilic addition versus Diels-Alder is how I keep them kind of in different compartments in my brain, right? Your brain has a really hard time holding on to information if there's no context. I feel like people treat the name of reactions as one extra piece of information they can't bother fitting in their brain. It's just too much. Without that little bit of context, without making that little bin in your brain that you're going to place all that information into, it's much harder to hold on to that sort of stuff, right? So just having these names in mind are very, very helpful in terms of like helping categorize things in your brain. Cool. As well as you're going to hear me say it a whole bunch, so then you at least know what I'm talking about, right? Cool. All right. We're going to start in on our next chapter. We're just going to kind of introduce things here. This chapter is what's called focuses on this property called aromaticity. Okay, and there's going to be kind of one star of the show in this chapter that we spend a lot of time discussing, and that is this 6-membered ring where every other bond is a pi bond. Okay, does anybody know the name of this one? Benzene. Benzene is a fairly famous organic compound because it illustrates a lot of cool properties which we'll discuss in this chapter. You don't use it so much anymore. You tend to use a benzene derivative because it turns out that it's absolutely just carcinogenic as all get out, right? So we try to get away from using it in the lab as much as possible. You usually use something with like a methyl group on there, just some other little tweak to that structure. But this is a very famous molecule right here. Importantly, because every other bond is that pi bond, right? We have that perfect spacing. And not only that, not only are all 3 of these bonds conjugated, but they're also in this ring here. So these pair of electrons can move freely, right? If we just draw our pi bonds, they're not stuck in those locations. They are delocalized. And in fact, they can delocalize themselves about that entire ring. Okay, so really when we're doing the structure of benzene, we should be good and not just include 1, right, but also show that it is in resonance, okay, where all of those pi bonds can move around in a circle. All right, I guess that was lazy. Okay, you will also, and not really in chemistry, but sort of outside of chemistry or maybe in the most introductory phases, see it written like this with this little dotted circle in the middle here indicating that those electrons are sort of moving about. We don't like this one though. All right, we don't really use it. It doesn't accurately keep track of how many electrons there are in that ring. So we won't really see this one too much, but it does kind of prove the point that these electrons are freely delocalizing about that network of p orbitals. All right, so we're going to talk a lot about benzene as well as related benzene, what are called benzene derivatives, some very similar compounds. The first step, sort of as always, is just nomenclature. All right, we're going to start with just benzene. Okay, so let's take, so first of all, if I just had this here, it's going to bother me how ugly that is. If I just had that there, that would be benzene, right? That's the IUPAC name of that molecule. So that one's easy. What if all of a sudden I put an alkyl group on there? How do we go about naming this compound? All right, we got our same 4 steps as always. Step 1 is to find that parent chain. All right, and our parent chain here will simply be benzene. All right, so our parent chain is that benzene ring, and it simply has that name, benzene. All right, so we're going to tack our substituents onto the front of that parent chain name. Again, the parent chain being benzene. All right, so step 2, let's find and name our substituents. All right, in this case here, we have a 3-carbon alkyl chain. So what would we call that substituent? A propyl group. Okay. Now we're going to number our parent chain. All right, but we get real lazy in chemistry, okay? So if we only have one substituent on there, what carbon are we going to number on that parent chain? That's going to be carbon 1. If we pick this thing up and move it to the other side of the molecule, what are we going to call carbon 1? Wherever we moved it to, right? So if there's only one thing on that ring, we already know it's sitting at carbon 1, so we don't bother numbering it. So what we're going to call monosubstituted benzenes. All right, we do not include the locant in the name. All right, so then this thing here, you wouldn't bother calling it 1-propylbenzene. This is just propylbenzene. All right, right, so let's just do 2 more examples real quick, and then we'll close it off there. All right, again, we're going to just look at mono-substituted benzenes for today. Right, so I look, my parent chain is automatically that benzene ring. Okay, so then we're going to find and name our substituents. Bromine we would call a bromo group. The cooler of all the substituent names for sure. All right, so then there's only one of them. We're not going to bother putting any numbering in the name, so this would just be bromobenzene. All right, if we look at our next example, we have our benzene ring, and then we have this 7-carbon tail here. Doesn't matter that that is longer, our parent chain is still that benzene ring. So then this we're just going to treat as a 7-carbon alkyl substituent, what we would call a heptyl group. So this would just be heptylbenzene. Cool. And we'll pick up with that next time.